Okay, so it's recording. So now let's go ahead and share the screen. Okay, so I'm sharing the screen. I am back at the Jupyter Notebook. Again, we are continuing to try to build a regression model to predict wine quality given 11 inputs, right? That's our wine quality data set. And so far, I've given you all the metrics that you can use to assess performance, such as this graph. I've already explained how to look at the data, real versus pred, and the loss function, of course, which we want to go down, and the R-square, which we would want to go up. So at this point, the R-square seems to be stuck at 0.29. I believe someone has managed to get a 0.33, but that's not statistically significant, let's say, right? We would all have to be getting 0.33. So it's not a reliable number, but this is how it works. We want to get it to go up, right? And our goal would be for it to be 0.98, 0.99, and then we would definitely have a good model and, we'd be happy and everything. All right, so I've shown you a technique called standardization, and that was meant to, it's usually you normalize the data. Maybe the equation I use, standardization, is not the right scaling equation. With machine learning, you almost never know, right? So maybe we should be doing normalization. I'm telling you that, okay? As you do your homework, consider that, okay? And it will be very straightforward to do it. All right, so what I'm going to do in this second half of class today is I'm going to go over other models, okay? So I've given you so far only linear regression, which is a linear way of basically building the model, but we want to add non-linear ways. So I'm going to switch for a second to the whiteboard to kind of give you some intuition of what that means, okay? And then after I've given you the intuition, we can start just writing the code for our architectures, which will be very nice because with this way of writing code, all we have to do is we're going to replace this instantiation with other instantiations. We've defined a class here, linear regression. We're going to define for every different architecture a new class. So we're going to say like a class called MLP, which is a multi-layer perceptron, a neural network with one hidden layer. We're going to do deep learning, which is a neural network with 2 hidden layers is what I'm going to define, but we could do it with 3, 5, 7, however many, 100 if you desire to do such a thing. And then I'm going to finally wrap up everything with like a technique, right, that I've looked in the literature and I've applied actually a couple of times, and I'm always really impressed with how it performs. So I'd be curious to see how it does for you guys. All right, and then after that, I've given you basically all the tools that I can give you, and I'll let, for your homework, and then I'll let you guys play with the assignment. And then after the assignment, as I said, we're going to run it on some benchmark things to see what was actually the highest R-square we could have gotten, okay? All right, so let's go ahead and switch to the whiteboard. Okay, so I'm going to stop sharing this one, and I'm going to share the whiteboard here. Okay, so just going to do a new screen. Okay, so I'm going to give you an intuition of what linear and non-linear models mean. Okay, now we are building not a classifier, but a basically we're fitting data, right? But it's the same idea, really. Okay, it's the same idea. So I'm going to use 2 examples, right? So I'm going to use an example here, just like this. And I'm going to use an example like this. So in both cases, we have a vector space. Our vector space is of size 11. That literally means there's 11 dimensions in this context, if we want to think of it in terms of geometry. Humans live in a space of 3 dimensions, spatial dimensions. One is time, right? But we can ignore time and just focus on 3-dimensional spaces, right? X, Y, and Z. Literally, that means that our R is R3. But when we do machine learning, we rely on vector spaces, which are of higher dimensions. And literally, the geometry is like thinking that there's more dimensions. This is a mathematical construct. I'm not talking about physics, obviously, right? And so it's just the math holds. The math holds and it works regardless if it's 11, infinite, a billion, you know, it can be any dimensions. The equations are still going to hold. Okay. So that's the important thing. Anyway, so that's the first thing I wanted to state. So the other thing I'm talking about is linear versus nonlinear. And what is the meaning of that? Okay. So there's two things we do in our currently in our knowledge. We are either building a classifier or we are fitting some data, right? So a class of, in both cases, if we're just thinking about a linear model, both situations mean that we are creating a line. Okay, that's what that means. Let me do it like this, just so you can see the analogy. Do you guys see this, what I'm doing? Right? That's a classification problem. And now over here, I'm going to do just circles. Imagine it's the same data, okay? Obviously, I won't be able to be as precise, but it's the same data. The only difference should be that these x's are circles, right, on this side, but it should be the same data. So in there's two objectives that are different. They're different here. In classification, now we use machinery, right? Machinery, math machinery, you know, equations and functions to build a line. That's a linear model, all right? So in this case, it's a line. And in this case, it's also a line. Do you see that? They both produce a line, the machinery, but the objective is different. Okay, this is what I want you to understand. So in this case, in the classification problem, we want to build a line that separates the data perfectly. In a regression problem, we want to fit a line. We want to create a line that fits the data. Okay, so in this case, it just so happens that they're both the same, but even they had different objectives. So now if we look at a slightly different problem, so I'm going to go back to red here. So they still can build, they're literally the same thing, right? So this one now is going to be, you see that, and this. Okay, make sense, guys? That's it. And then on this side, same thing. Imagine they're exactly the same, right? But the only thing that changes is that these x's are now zeros over here. Okay? In a classification problem, I want to separate. So the machinery builds a line. That's a linear model, right? But what should the line look like here? It's a line that fits the data like that. That's the perfect separating line. If I draw this line, that's a bad classifier. Why is it a bad classifier? Because yeah, it's good at classifying the x's, but it's getting a lot of errors here, right? It's marking these as x's when they should be zeros, you see? So the best line is this one. In a regression model, we don't try to separate because there's nothing to separate. There's just the data. So what should be the perfect line here for a regression model? It's this one, right? The one that best fits the data, like the general direction. Because the goal is to predict. If I have a value here, let's say here, right? Where do I want it to predict a zero? Well, it'll be on the line because that's the inference. And the real data would probably be like around here, around here. So it's a good model. That's the best one. If I did a regression over here, oops, and we'll come back to this when we look at theory, but if I did that model, that's a worse model, right? You know, if you're trying to predict things, the stock market, right? This is off the mark compared to this one. The error between this line and these values is much smaller than the error between this line and these values. Do you guys see that? So in regression, we want to build this line. In classification, we want to build that line. In both cases, though, we build lines. Do you see that? It's like the machinery that we use in math to build the lines. What is the equation for a line? Y equal mx plus b. Surprisingly, it looks a lot like, right? Which is the general equation that we use to build things, right? In machine learning. Whether this is the weights and these are the inputs, and then we have the biases, so-called parameters. Okay? Question? All right. Anyway, so keep that in mind, please. All right. So hopefully you understand the difference between classification and regression. Now, what is the difference between linear and nonlinear? So here I'm just saying, is this a line, a straight line? Yes. Is this a line, a straight line? Yes. So what that means is that is a linear model. And that is built by doing y equals w. I'm going to the neural network realm now, plus b. Okay. What makes it nonlinear is if this is no longer a straight line, but some kind of a curve or a much more complex non-line. Okay. And to create those things, we are going to have to then say something like not y, but usually h, which means hidden. And then we run this through, oh, sorry, let me do f instead, a generic f. So we're going to have f, and the h runs through that f to become y. Do you see that? We're going to add a function that this linear thing that we still create now needs to go through some function that we're going to define and then produce the y. But this, plus the fact that we have multiple layers, will give us a non-linear model. Okay, and we will code this in a second. Now, how does that look? All right, let's go over here. Switch to red again. So I'm going to do the exact same thing as before. I'm going to show you guys. So let's say that my data is now that's my data. Is there a straight line that gives me perfect accuracy here? No, right? There is no perfect line. If I do probably like that, maybe, I'm still going to get some errors. Do you see that? But my linear model can only give me this because it's like a mechanism that can only build these things and nothing more. So I need something else, other mechanics, to build something that is not a line, nonlinear, right? That's what that's called. So I'm going to use a neural network with hidden layers, and I'm going to build, for instance, a curve. Now I can build like just a curve like that, right? But that's not perfect, right? It still gets some errors. Or I can build a very precise curve to the data. Notice like there. Do you see that? That is very precise. How do I build this thing? Basically by adding little pieces together until I make this very curvy line. It's like almost too precise. And that's another problem in machine learning called overfitting. If you build this line, you build it for the particular train set, but once you apply it to the whole population, it may not be exactly like this. You see that? So it's a trade-off. You don't want to be too specific, but also a line may not be, obviously, it's not good enough, probably. Got it? So that's hopefully the intuition of what we're going to do next, right? So we're going to go from where we were of just building that straight line like that. That's all we could do with that model, to the new models, MLP, deep learning with 2, 3, 4 hidden layers, right? All of these models allow you more flexibility to make these more curvy, and so on. That's basically it. All right, and then of course there's a whole discussion of activation functions and things like that. We'll discuss that in a future lecture, okay? But today the focus is really just the architectures in general, and then I'll give you some things to play with. Yeah, and that's it. So any questions about the intuition of what we're going to be doing? Make sense to everyone? Oh yeah, please.
What's the use case of the non-linear architecture?
Pretty much everything. So the use case, if I understand your question correctly, is when would a nonlinear architecture be better than linear, right? The world is complex. And the relationships are not always linear in general. Another way of putting it is, if you have a problem and it's a lot of it is linear, is like, oh, it's an easy problem. That's kind of how people think. But a lot of things, linear models would just not work. Yeah. So, I mean, the example is like, why is there so much excitement with AI, right? It's because AI has basically, when you say deep learning or neural networks, nobody is assuming it's a linear model, right? And so they're throwing more at it. Did I answer your question? Yeah. So the majority of it, but I mean, I'm working on a project right now and it's linear pretty much. And I'll show you a nice little trick at the end today where we're going to have a linear plus nonlinear model. So it's like we're going to build a linear model and also a nonlinear model and let them work together, kind of, because there may be that the majority of it is linear and there may be just a little piece that's nonlinear. And so we can build that as well. Okay. But yeah, so but in general, neural nets are meant to be something that goes beyond linear. Okay, that's the idea. All right, so this is the whiteboard. So basically that was the intuitions. Let's go ahead and switch over. So I'm going to switch over to the Jupyter notebook. All right, so as I said, if to kind of relate, this thing here is what was building straight lines. Now we're going to create new classes, and these are going to be nonlinear. So I'm just going to copy this one because it's got a lot of reusable things. And this is what I love about this approach. This approach is like one of my favorite things, like in the world. So I really like this because, you know, we can build our models, very complex models, just by changing this and play with it, right? And it's very reusable and so on. And it's sometimes these models are made up of other neural networks inside, and those can be classes too that we use inside. Okay, so it's very nice like that. All right, so let's go ahead and rename this one. So I'm going to call it an MLP. So MLP stands for multi-layer perceptron. It usually means, in general, a neural network that has an input, an output, and one hidden layer in between. If I talk about the linear regression in terms of a neural net, basically has, remember, because this is an exam type question, one input and one output, and that's it. No hidden layers. Okay, guys? All right. So now we're going to define the architecture for our MLP.net. What's going to happen down here is, this is what's so great. All the code stays the same. And all we have to do is, let's, comment out this one. And we're going to make this one MLP _ net. And that's it. We invoke the new instance, right? The new instance of the class. So, but obviously we need to define it. So I'm going to do MLP _ net. And now we're going to think. So first we're going to write the code, and then we're going to draw the diagram and run this again. And it's not guaranteed that it's going to be better, but hopefully the neural nets are going to start improving our performance. Our performance seems to be around 29 to 33%, 33.29 to 0.33 R square. We want to improve it. All right, so let's take a look. So MLP.net or _ net is a class. It should inherit an init module once again. We need an init and a forward. We already have in the init the x means and x deviations. Then we're going to do the initialize the inherited class. Now we're going to build, this is going to change because now we have different architecture. So we're going to add the activation, which will be activation, I was going to call it activation 1, which means that it's the, once we do the prediction through linear, we're going to run that data through a function. Okay, in this case, there are many activations. We are going to use the sigmoid activation. Okay. After that, we are going to need another layer. So it's going to be self.linear 2. Okay. And this is going to be also an nn.linear object. But now we have to worry about the number of neurons in each one of these. So the first layer, so let's actually, before we do this, let's switch to the whiteboard and think of the architecture. Okay, so in the linear example, the linear regression, it looked like this, right? Linear was 1, 2, 3, ... 11. 11 by 1, right? And this is fully connected, yeah? That's the linear architecture. The multi-layer, MLP, the one we're drawing right now, MLP, should look like this in general. This is the input layer. This is the output layer. The output layer has 1. The input layer still has 11, but now we are adding a layer in between called a hidden layer. Okay? And this has 11, right? These are fully connected. So that means every neuron is fully connected to all the neurons in the next one. And this one is also. Now, this is where this is called architecture, and you're the architect, which means you can decide how many neurons and how many hidden layers you're going to have in your architecture. So how many do you have? You have 2 choices here. Since this is 11 and this is 1, this could be a number in between those 2, or it could be a number a little bit higher, but just don't make it too high. You don't need that much power, if you will. So you could make it 20 neurons in here and try it. That's fine. I would probably, what I think I did before is I just tried 8. But 6 could be a better. I just don't know. There is no way of knowing. You got to try it. So let's say 8, right? That's the architecture. I will say this. When you have something like images, which are really big, like 784, and then you're predicting like 10 classes or something, you want to take a good approach is to take a funnel approach, which means that the next hidden layers are always decreasing by a bit. All right. That I can tell you if it's really big. However, when you have these really like small things, you can take it a little bit higher. I would say if this is 11, no more than 20, or you can try like 6 to 8 is what I would try first. But it's difficult. I mean, there are frameworks that you can build that would suggest which one's the most optimal, but it's almost equivalent to just trying a whole bunch. Does this make sense, guys? So let's assume that we're going to go with 11 to 8 to 1. Or you can go 11, let's say 7 to be a little bit different from the other class. Right, 11, 7, and 1. So now the key is to code this in the class that we're defining, right? So let's do. Okay. So how would you write that in here? That's the key thing, right? You can write whatever you want. You just have to know how to do it. What do you guys think? So this is obviously linear 1, and then we have linear 2, right? So linear 2 implies the hidden layer. So then this should be oh yeah, go ahead. 11 to 7, very good. 7 to 1, very good. Exactly right. Exactly right. Yeah, that's it. That's how you build your architecture. All right, and so that's the multi-layer perceptron. We've done the activation. Now remember, all we're doing here is defining the variables. We actually have to build the architecture here, and it's just a sequence. So This is not going to be y pred anymore because y pred is the last one. Instead, we can just use x and modify that variable. So we're going to start with linear 1. So x goes in, right? It gets standardized and it becomes this x. Then that x goes in here, goes into linear 1, which is a linear of 11 to 7. That's correct because our inputs are 11, and now we're just shrinking it to another layer that's 7. Right? Then, to make it nonlinear, we have to add the activation. So that means we're going to do x equal self dot activation 1, and that goes in, and the x goes there. So what happens there is we're mapping whatever the output was into a new output given this function, a sigmoid. Right? So I'll give you the simplest example. Actually, a better function is something called ReLU sometimes in machine learning. So I encourage you guys to test that one. ReLU, like that. It's called the rectified linear unit, okay? And intuitively, it's called the hockey stick. So what does that mean? If we go back to the whiteboard, it looks like a hockey stick. So what that means is if your data, let's say the data is like this, and then so the data lives in X, and now we're going to convert it to Y. So what this means is if the data, this is negative, obviously, and this is positive, right? So if the data is negative, you always make it 0. Okay. But once it's positive, it just remains what it is. And so if it's 1, it's 1. If it's 2, it's 2. So it's like that. So that's why it's called a hockey stick, because it looks like a hockey stick, supposedly. Does that make sense? So it's a good intuition. And this is called the rectified linear unit, or so-called ReLU. A lot of machine learning techniques use this activation, as it has been found to be pretty good. Okay, but I'm giving you the sigmoid. Sigmoid's a little bit different. If we compare it to this thing, sigmoid does that between 0 and 1. Right, so that means as the values are negative, they're close to 0. Then as the values become positive, they're close to 1, basically. Does this make sense, this intuition? Yep. So these are called activation functions. There's several: tangent, sigmoid, ReLU, GeLU. So we'll play with some of these later, but that's what's happening. So the values are being converted from one range to another range. That's what gives you the nonlinearity. And so that's what we're doing there. So we can go back to our section over here. Okay, so we standardize the data in the forward function, then that data goes into the linear 1, which gets converted here. This X goes into the first activation, okay? Now, once it comes, this is important. So let me go here and here. So what that means is activation 1 happens here, okay? So X goes in, right? Then it goes into here, right? That's linear 1 because it's going from 11 to 7, yeah? And then here, that activation 1 that you saw is happening here, okay? That's where it's happening. After that, it goes from 7 to 1, but it first needs to go through that activation 1. Do you see that? And then you could have an activation 2 here if you wanted to. It just so happens I'm not adding an activation there. Why? I mean, I don't know. Try it for your homework. Right? Try it. At the end of the day, just get that. I don't care how you do it. Get an R square that's really high, right? You're the architect. Figure it out. That's the homework. All right, so let's go ahead now and go back to the code. So I'm going to do... Okay. So, all right, so we added the activation 1, but we haven't added the 7 to 1. That's going to be Y pred So we can invoke self dot linear 2, right? And that takes in the previous x. Remember that that x after activation 1 is now a vector of size 7. So it'll fit here 7, and then it will be converted to 1. Got it? Now, a trick is to add a layer called dropout. So I'm going to add that now. And so let's do self dot dropout, just so I give you all the tools. And dropout is, I'm going to set it at 0.25. You can change that parameter. So what is dropout? First, let's say that I'm going to use dropout after activation 1. So how do I do that? I say x equals self dot dropout. This was invented by Geoffrey Hinton. Oh, you need to plug in always the x inside. Okay, otherwise it wouldn't do it, right? So Geoffrey Hinton, who is, you know, the godfather of AI or something, he invented stochastic gradient descent, basically, one of the biggest contributors to machine learning or deep learning. He coined the term deep learning. He also invented this technique dropout. It's very clever, very easy thing actually to implement, and could be very useful. So what does it mean? So let's go to the whiteboard again, and let's define dropout. So I'm going to go to a new line, new sheet. All right. So what is dropout? Let's say that you want to do, you want to build several architectures, right? So you want to try several. So you're going to say, okay, so it's 11 and it's 1. So one layer could be 9, right? Another one could be 20, right? Another one could be 3. So you would literally have to code all of these, correct? You would have to try one or the other or the other. With dropout is a very clever thing. What you do is you look at the one that's the biggest, right? So this is 21. So then you do 11, 20, and 1. But you're applying dropout like here, or you apply dropout here, right? So I encourage you to play with that. Notice that I only applied it here. Maybe I should apply it here. Okay, try it. What's the intuition? And I said dropout with 0.25, right? So what that means is that every epoch, the neural network will drop 25% of the connections randomly. You see that? You see how that's equivalent to trying all 3? Because sometimes it's gonna drop certain ones and it's gonna be like it's got 9 in there. You see, or other times it's always gonna be maybe like 9, but they're shifting, right? They're moving around at least. So you can play with that dropout value. And so what that means is that you're basically, as you're running different iterations, you're trying different architectures, because you go from being fully connected to only partially connected, where some of the connections no longer get considered. So what happens is, as you're dropping connections, you're still updating the weights. Every time you update the weights, but you update it, almost think of it as like roads, right? So I'll do an example of roads. So one time the roads are like this, and you update the weights. But the next iteration, the roads are like there, and you update the weights. And the idea is that you're forcing the model to like learn with less. You're like, but randomly trying different architectures, and eventually it finds the best set of weights by trying different models. Okay, so dropout, that's the intuition anyway. And yeah, it works sometimes. Okay, it allows you to try different architectures. Okay, makes sense? Because at the end of the day, the weights kind of reflect the architectures that you had in there, even though at the end, the model would be fully connected. Okay, so the weights would be like, okay, it's always 0 for this connection because it was never a useful one. Okay, so that's anyway the idea. So you can try dropout. Any questions about dropout? Yeah, go ahead, please.
Like the way it works, seems like an intersection. Try something else.
Because remember, at the end of the day, you're measuring performance, right? So you're minimizing the loss, right? So you're just basically, instead of updating all the weights, it's like you have fewer connections. And so you update the weights for that epoch that are connected, basically. But the next iteration is going to be another set of connections. And you update the weights based on that. And you try that multiple times. And eventually the idea is that, you know, it's like the model learned with less maybe. And I mean, in theory, it should be better weights. So, because you're trying, it's like you're trying different architectures is the way that I would describe it. Do you see that? Maybe if you make it like an exaggerated case, so it's like drops 70% of the connections, right? So then let's take one like this example or this example, right? Like that. So it can only try, like it totally ignores the middle connections. It only tries either the green connections or the red connections, right? But remember that at the end of the day, it predicts a value, the pred. And that pred gets compared to the real. That's still happening. So what happens is it never looks at the middle connections, let's say in this exaggerated example. It tried only the green and the red. And it turned out that whenever it went through the red connections, it was bad performance. So what happens to these weights in general? They're going to be pretty tiny. Whereas these green ones, whenever it went through here, the results were better. So these weights always got what? I mean, this is an exaggerated weight, but 0.5, 0.4, they're better weights. You see that? In the exaggerated case, if it uses all the connections, a ton of them, what's going to happen is like this importance maybe gets buried. And it, you know, you steal some of these weights into these and you get a worse model because it's like all over the place. You see that? So it's like it's forcing it with less. And that's the equivalent of me doing all these architectures. At the end of the day, maybe this was the best architecture. But I only built this one and I made it fully connected. So it had to adjust the weights for all of it. Do you see that? Whereas here, I'm trying all of these three by having fewer connections. And so it, you know, at some point it will try the middle ones. And it just turns out that they're not great, right? And it tries these, and these were pretty bad, actually. But it's able, I guess, to zero in on a set of connections, if that makes sense. Do you get it? I mean, it's the equivalent, as I said, of if I can guarantee you, if you try this with 9, this one with 20, and this one with 3, one of those will be better than the other two. Do you see that? This only has 3 neurons. This has 20. This has 9. But how would you have guessed that only 3 neurons in the hidden would be better than 9 or 20? Unless you try all 3, measure the performance. You see that? A quick way of doing that is trying dropout. Because dropout, if you build a 20, will drop some of the connections depending on that 0.25 or whatever it is that you're putting in there. So you should try some people will try 0.25, then we'll try 0.50, but that's easier than creating a ton of different architectures. Do you get that? And now this is only with MLP. Now think if I do this with a deep learning of 3 hidden layers, right? Then I should put a dropout here, a dropout there, and just keep trying. And it's a quick way of trying different architectures. Got it? Does this make sense? Yep. All right. All right. So anyway, so try the dropout if you'd like in your homework. Keep in mind, I'm only putting it, no, you should understand this part, right? It's going after the hidden layer. Maybe, right? You need to do that. Okay, but I'm leaving that to you. Okay, so that's part of the homework. At that point, I want you guys to start playing with this. Okay, you should be able to figure it out. All right. All right, so that should complete our MLP, correct? Would you agree? Is it a neural network? Yes. It's got a hidden layer, goes from 11 to 7 and then 7 to 1. And we definitely have an activation function, right? Right after the 7, we have an activation. That makes it a neural network, okay? All right, good. So now let's go ahead and run this. And while it's running, let's create the next architecture. All right, so we're going to create. So we just got 2 more architectures to create. And then hopefully you guys can play with this and see what results you get. Any questions? All right, so let's go ahead and run this one. Okay. Let's run the train loop. And let's instantiate this new loss and our new architecture. Oops, okay. Where's the error here? Oh, yeah. So this is a mistake. I need to create a variable. So I did this totally wrong. Should be NN. I forgot to define it, right? So this is capital D, drop out, and then like that. All right, that should be the correct, okay? So hopefully you guys can see. And then down here, we call dropout the variable, right? Which is instantiated as nn.dropout, okay? So now hopefully it'll work. So let's go ahead and run it. Okay, so here's the moment of truth. All right, it's running. There we go. You see the loss is now 12 instead of 33. So something. All right, so hopefully this will give us better results. Obviously, running it with 400 epochs, 1,000 epochs, and more. Play with the learning rates. Hopefully we'll get, I remember in the other class, we got to almost 0.4. All right, so, but that's still not a good R-squared. Okay, so we would want 0.80, 0.90, something. But I mean, the problem may be that that's what we get. Any questions, guys? Everyone with me? Say that again, sir. What?
I see where it is.
Oh, you got it? Okay. Yeah. All right. So while it's running, we're going to do the next. We got 2 more architectures to do, right? So we've done a linear model. Now we're in the nonlinear world with a multi-layer perceptron, but this is not yet deep learning. What makes something deep learning by definition is to have 1 more layer than 1 hidden layer. So 2 hidden layers. That's deep. That term was also coined by Geoffrey Hinton. Okay. So let's go ahead and create the new architecture. So you can simply just copy the MLP architecture, and because we're just going to be extending it, as you might imagine. Right. So that's the beauty of this. So now we're going to create a new architecture here. And these are totally interchangeable, right? And you can see how nothing needs to change except for this class. So let's name it DL. And I'm going to add a comment here. And I'm going to say that this one is deep learning with 2 hidden layers. All right, so DL net. It inherits an N module. We pass X means and X deviations. We initialize the superclass or the inherited class. And now our architecture is going to have 2 hidden layers. So that means I'm also going to switch up the activation to ReLU here, just to try something else. So that's ReLU, the hockey stick. I'm going to have, so it starts at 11. And now I'm going to say that it's going to go from 11 to be different from the other class. Let's say 11 to 9, then 9 to 6, and then 6 to 1. Okay, so let's make it 11 to 9. So this is now 9 to 6. Okay, right? And I'm going to add now, so there's going to be an activation after 9 and an activation after 6. So we need to add another one. So I'm going to say self dot activation 2, and that's going to be equal to nn dot. You can try other activations such as sigmoid, tangent. Okay. Okay, and then yeah, so we do linear, ReLU, linear 2, activation 2. And we need a last one, right? So self dot linear 3. nn dot linear. And what are the values for that? Yep. Right. Very good. Good catch. And oops, we are. And then what are the values here? 6, 1, right? Very good. Yeah, you guys are getting it. That's it. I mean, obviously, we're going to make much more complex architectures, but this is the game, basically. If you master this, it's going to really help you to write your code. You'll be able to implement a transformer if you follow this. Eventually, it really starts to pay off, to be very disciplined here. Okay, so that's actually our last code. Hopefully, will be GPT. Just a transformer side of a, sorry, just the decoder side of a transformer. Hopefully we'll get to that. All right, so and let's leave the dropout there. We can use it wherever we want. So 6 and 1. So now obviously the forward, you guys can tell me, right? So X linear 1, then X activation 1. Let's not use dropouts. I won't use them, but you guys can add them whenever you need to. So after activation 1, we call activation 2. Only this is only a like a intermediary layer, right? So what do I do now? Huh? Self what? Act 2, right? Input X. Okay, very good. Self dot linear 3, right? And the input is X. Perfect. You guys get it, I think, right? Good job. All right, so yeah, that's it. So linear 1, activation 1, linear 2, activation 2, linear 3, and then you can add dropouts wherever you want, usually after, right? So you can do it after the input, after, and try it. Try it. I mean, it's experimenting. And then your YPred gets returned, okay? And congratulations, welcome to deep learning. Because you just did your first deep learning. This is a real deep learning architecture. You've done it. Right, good job. And also it seems like the training finished, right? So let's see. It got a 0.31. So let's run the R square. Remember, this is an R square with a multi-layer perceptron, correct? We were at 0.29 with linear. 0.26, not so great. What is yours? 0.27. Huh? Yeah, it's the same data set. Oh, it might be that the model is still the same. and so it's just updating those weights from before. What I'm gonna do is, this data seems problematic. So I'm going to clear the output and run it again. Okay. So, as I said, you gotta, I'm giving you the architectures, but you gotta make that R square higher. Okay, so I'm running it again. Let's see. You guys should also be running it, hopefully. And if you get an R square that's better than 0.33, let me know. So while it's doing this, let's add the last architecture, okay? So this is like literally the last architecture that that's different. Obviously, I can do deep learning of 3 layers, 4 layers, 5 layers, etc. But that's just adding more layers. I do have an additional architecture, which I mean, it's called usually a linear plus nonlinear model, okay? So let's add that in. And think about what it is. Okay, guys, so let's follow along here. We will once again copy this one. But now we are going to invoke or change this to linear plus nonlinear. All right, that's the new neural net. It once again, it inherits the class from PyTorch. We do x means, x deviations. We got x means and x deviations here. I'm going to delete these because I'll just get confused. So I'd rather just start with a clear. Okay. All right. So now it might be that I implemented the standardization incorrectly. So just if you doubt it, just do this and that's it, right? You know, just it'll take the x as is and see what the performance is. Maybe standardization is should not be used here. I don't know, right? So that's what you need to play with. All right, so what is F1 plus F2? It's literally 2 functions, right? Both of them predict, and then the values are added together. But because that is happening, the weights are adjusted based on the fact that there are 2 like neural nets predicting values and being added together. You see, so it's a different set of weights. So the way that we can write it in is, let's go over here and first initialize it. So I'm going to say F1, okay, and that's going to be the linear model. So it's very similar to the linear. So self dot F1 linear 1. Okay, and what is this one? This is just an NN dot linear that goes, it receives inputs of size 11 and it predicts 1. That's it. But then we're going to create another function F2. And this could be a deep learning, this could be an MLP. I'm just going to do the basic MLP and I'm going to let you guys play with this one. So I'm going to call this one self F2 underscore linear 1 because it refers to the second function. And this is going to be an NN dot linear. This should be uppercase. So linear. And then here it's going to be 11, but it's going to have a hidden layer for this F2. What is it going to be? Whatever you want it to be. But yeah, it could be 8. But in this case, just to show you that you can, I'm going to make it 14. Okay. You need to change this architecture to whatever you want. So it's going to be 11, 14. And then we need to create the self.f2 activation 1, right? Activation 1. And that's going to be an NN. Now, which activation should you choose? I mean, try different activations. Here, I'm just gonna say sigmoid, okay, guys? All right, and then we need to wrap this up. This is an MLP, so then we have a self dot F2, linear 2, right? Linear. Oh, sorry, this should be 1. I made a mistake here. So it's for F2, but it's linear 1. And so this one would be linear 2. Okay. Equal NN dot linear, right? 14.1. Exactly. You guys see that? It's basically two things, the linear and the MLP, but they both take in the vector 11. X is the same going into both, and they both predict. But after they predict, you add the value. And that's the output that comes out. So the weights obviously are going to be adjusted to reflect this new architecture. Okay, so obviously this is only the initialization, so we need to build this architecture here. So first, we're going to build the F1 architecture. F1. So that's F1 equals self dot what? F1 underscore linear 1 parentheses. What goes here? X. Do you guys see that? All right, so X goes in and it predicts F1. Then we do F2. And this is going to be F2 equal self dot F2 underscore linear 1 X, right? But it's an MLP, so then it's going to be F2 equals self dot F2 activation 1, right? Yes? All right, and what goes in here? F2. Do you guys see that? This one, right? Does this make sense, guys? Goes in here. Then we do F2 equals self dot F2 underscore linear 2, right? That's the next one because it's 11 to 14, 14 to 1. And what goes in here? F2. Very good. All right. And that's it, right? So once we do this, the last part is to force both of them together to predict a good value. So it's going to be F1 plus F2. Do you see that? Some people could put like weights on F1 and F2, but that makes it more complicated. This actually is basically, so now what's going to happen? It's going to predict, let's say that it predicts 7 here and it predicts 3 here. So 7 plus 3 is 10, but the value was 6. So the weights are adjusted accordingly for both neural nets because they're both in the torch graph, the computational graph. Okay? And that's the linear plus nonlinear. Try this one and see if it works, okay? Any questions? This is the last architecture I'm giving you today. And that's basically what I want you to play with. All right, so now that one is also constructed. So now all that remains for today is check out our results. So we were running, it finished with the MLP, right? So let's see what it predicts. 0.28. And what did you guys get? 28. All right, so we're not getting 33. Let me actually, I'm gonna remove the, so I'm gonna try a DL net, but I'm gonna do it without the standardization, right? So I can turn it off just by doing that. So this one is DL net, right? So then I'm gonna do that. And then here, before I run the main loop, I'm gonna change this to DL net. Comment this one out. And I'm gonna call this DL net, okay? Everyone with me? I just, the standardization. So I did it for DLNet because that's the one I'm running. See this line here? Because we named it X, you know, by commenting it out, we can still use this X and it just, we use the unscaled one. Got it? Yeah, so let me run it. So DLNet, right? So now we're running a deep neural network and let's just let it, yeah, let's let it do its thing. Yeah, go ahead.
Why did you remove standardization?
Because I don't know why it's not doing well. In theory, standardization should always give you better results. But machine learning is like this. It's weird. So try it without. And you got to get a feel for, so at some point, you got to convince yourself in your mind and say, okay, standardization is better. I'm going to leave it in. Which one? You got 0.36 with what? With standardization, 0.36, and which architecture?
Deep learning.
Okay, deep learning. All right, so exactly right. So we're at DL and with standardization 0.36. So what would you do now to really answer the question? Leave deep learning, comment out standardization, run several experiments. If the value is less than 0.36, right, then that tells you that standardization is the way to go. Do you guys see that? This is the nature of machine learning. Yeah, go ahead.
I found out the standardization.
Yeah. 0.28, right? So what should you do now, knowing what she said? Put it back in. Perfect. So put standardization back in. As I can tell you theoretically, standardization or normalization will in general give you better results. Okay. So which was my intuition. So hopefully, yeah. So it should give you you should add it back.
Sharing this out every time we run.
In theory, yeah, because the model may keep the weights, yes.
Okay.
But
Is
it
there a way
does.
to write something that would clear it out without us having to remove.
Yeah, there's you can do kernel and you can do run all again, restart and run all. So it clears everything and reruns it.
I don't know if there's a command that we could put inside here that we could just run that one thing and just clear out the weights.
No, just do this.
Okay.
Yeah, do this. I mean, there might be, but I don't know.
I just didn't know if we had like, 500 lines, you know what I'm saying?
Yeah. I get it. So, but yeah, this is, there might be, I don't know what it is. Okay, so yeah, so do this. If anyone is at the point where they just want to run the linear plus nonlinear with standardization, go ahead and try that one. I'm curious to know what you get with that one. Okay, so that's low. Now add back standardization with DL.
I just read it without it and I got 0.30.
Okay, so lower, right? Okay, so then add back standardization. Also, make sure that you guys are looking at the visualization that we had down here, right? See if that looks better.
So with standardization.
Yeah.
Deep learning, it went up 0.7. So it's in 35.
I got a nearly 40%.
Okay, with standardization and DL, right? So as you can see, yeah, I mean, it's what we want, right? But we're still at 0.37. So keep, this is your homework. Try to get the best results that you can. And then, like I said, after we're going to benchmark it with some tools we've got to see what would have been the theoretical limit. But yeah, that's just your homework. So play with it. Also, remember, we're only running like 200 epochs. In theory, we might want to try way more. Change the learning rates. Those are all the parameters you should be changing. Yeah, I got 0.33 with DL and no standardization. So I think, in conclusion, standardization is working. I'm going to add it back in, but I'm going to run linear plus nonlinear now. We've got about 7 minutes. Should be able to get that answer. Sorry, say it again.
Way to run that.
Yes, please.
Well, I'm doing it right now with.
Did you run it, Jacob? Did you run it?
I read it, but I had.
0.36. Okay, so seems to, yeah. Yeah, so this may be the limit. So we, try. That's the whole point of the exercise. See, remember, change the learning rates, try more epochs, try dropout, try more layers in the deep neural net. I mean, there's lots of things you can try. All right, so I'm going to add a 0 to the learning rate.
I did that and it just blew it out of the water.
In what sense?
It went terrible.
Terrible?
It went worse.
You might just need more epochs, yeah.
That was, yeah, because I did that with only 400.
So we've got 6 minutes, so I'm going to run
So it's.
linear plus non-linear. You can also try like instead of more zeros in the learning rate, fewer, right? Like this, like try that as well. Okay, I mean, yeah, try. All right, so that's basically the class. I've given you hopefully all these architectures. You have a goal, right? To get 0.98 R square. Good luck. Yeah, go ahead. Yes, try more epochs, try different learning rates, try different architectures. It can be that like the highest will be like 0.43, in this problem. Like I said, after the homework, I'll use these other tools I have to see what the best score might be. Okay. But there's one thing that, oh yeah, go ahead. Lucas. The other class got almost 40.
I got that with you.
What did you get? Yeah, so you're at the high end of where they were. I think it wasn't 40. So you're exactly keep at it, right? The whole point of this is to like try everything that you can. There's one thing about this data that I don't like, and I think I've mentioned this. It's a rating. So we are predicting like a 7 or a 6 or a 5 or a 4. We're not predicting 3.5. You see that? You see what I'm saying? Now, in theory, the model should be able to learn 3.0 or 3.001, right? So I haven't done anything to the last layer to force it to be, instead of 3.7, either 3 or 4. You know what I mean? But maybe that's something that should be looked into. Okay. So all these things are things to think about as part of the problem, when we're addressing. Maybe at this point, what I would say is go and read a research paper, right? When I'm building a neural network to predict ratings, what should I do? You see what I'm saying? And then you start digging deeply into how to solve it. But hopefully you're starting to get an understanding of what's going on. We will benchmark it with like regression trees and other stuff. So we'll be able to get a sense of what should be the best score. Okay? So mine is still running. I'm gonna stop the recording at this point, and we're kind of done, but you guys know what the homework is. You 42 you got? Oh, okay. All right, so I'm gonna stop it now.